Good morning, everybody. I will be presenting you a work done with Bastien Cazot in Montpellier and in collaboration with Thierry Lecros at the University of Rouen. This talk is about some problem related to computational biology, where people are sequencing genomics data sequence, and they are getting a lot of short reads. And to assemble those short reads to recover the real sequence of the whole molecule, they do some assembly. And usually when you have a lot of short reads, assembly algorithm resort to the Bruijn graphs. Okay. So this is one specific data structure for assembly method. But in reality, this was introduced by Pavel Pevner for de novo assembly problem. But in reality, when people get the raw sequencing data, they already perform many operations before the assembly process. In particular, they filter the data, they remove some part of the data, and they correct the data due to the presence of sequencing error from the machine. Okay, so some time for that, to do that quickly, they build some indexing data structure, which you all know in this community, like suffix tree or whatever. There exists algorithm to build the Bruijn graph directly from the pure data, and but there is a contracted form of the Bruijn graph for which there is no direct algorithm to date. And our purpose was to use the fact that some indexing data structure was already built for those data, and that we could construct the Bruijn graph from the indexing data structure. So this would give other algorithm to build the Bruijn graph, and in contracted form or not. And it will also set up links between the indexing data structures that you know, like suffix trees or suffix arrays, and which are usually functionally equivalent, and another data structure which is the Bruijn graph. So in this talk, I will consider only the suffix tree because it's the most well-known, one of the well-known data structure, and it's easier to show images and example on a tree than on an array. But we could do it for other data structures. So our problem is that you are given a generalized suffix tree for the input set, which is a set of words, and it indexes all the factors of the set of text. And we have the question, how do we build directly the assembly Bruijn graph from this data structure in uncontracted or contracted form? So this is our problem. So I will reintroduce slightly the suffix tree and the Bruijn graph and go to the algorithm afterwards and make some conclusion in the end. So we had already two introductions of the suffix tree thanks to previous speaker, especially yesterday. Here we will consider a suffix tree for a set of words and not a single word. So I will have a running example throughout the speech, which is this one, and we will use one color for each different word. So orange, blue, black, red, and green. And the size of the input is the sum of the size of the input strings, and this is denoted like this. So here, for this input, the input size is 31 because it's 7 plus 5, and so on. I will keep to this example. But first, the usual representation of the suffix tree for a single word, this one here. General, we make the assumption we have a separating symbol at the end, which makes the set of all suffixes indexed by the whole complete branch of this tree prefix free. And we have this representation. In this representation, some of the ages are only labeled by this dollar symbol, special symbol, and they only give this information that you are at the end of the suffix. However, you could avoid this, and in this case, the branch here, for instance, labeled by a single dollar, you have the suffix, the starting position of the suffix, which is 6 here, which will go inside the internal node. So this will make, in this representation, the internal node, we have some label for the start of the suffix, and it will be a node with out degree of 1 external edge. So this is another representation. Okay, a bit shorter. So this is for our input example, the generalized suffix tree. Okay, so the generalized suffix tree, for instance, here this node represents the word A, and it is found in many positions, all those positions, but it is found as a suffix of 2 words, which is starting, the red word starting at position 6, and the orange word started at position 6, which you can check here. AA, the position 6 in the orange word, is the start of this word. Okay? The nice thing with those numbers is that we don't represent the suffix links here, but of course, the suffix link, for instance, from B, C, A, represented by this 4 red. By the way, I apologize for colorblind people. I'm sorry for that, God. The suffix link will go to the red 5 node, because this number is a suffix. So the next suffix in the red word will be the next number. Okay? So that's easier to see. Now the doubling graph. So the doubling graph, you may have several definitions, but we'll get one. The nodes, you break the input words into k-mares for a given integer k. So the nodes will represent the k-mares, which are present in the set of words, input words. And an arc, will link 2 k-mares, directed edge, 2 k-mares if those k-mares overlap by k-1 symbol and are in the same, in at least one of the sequence of the input set. Okay, so you have 2 conditions, the overlap and the presence in a sequence. You could remove the second condition and you will get a slightly different definition. So we'll call the one with the 2 conditions dbg plus of order k, and if it's not, it would be dbg minus. We can do all algorithm for both, it's no problem. And for our example, if I take the dbg plus definition, you have for k equal 2, you will have bb, ba, all those nodes are the possible k-mare in this set of words, and you will have only the solid edges. Okay, so dotted edges are for the other definition of the Bruijn graph. Okay, so for instance, you will have BBA at the start of the orange word. You will have therefore BB solid edge BA. Okay, this is a Bruijn graph, but you don't have CB solid edge BB because CB here is not followed by B in some words. Okay. So we will stick to the definition with solid edges only, which is much shorter. Okay? So now, how can we get from one to the other? So, of course, all the k-mares are represented in the suffix tree. Okay? So therefore, either as some explicit nodes or by some point on the edges of some going to some explicit nodes, some implicit nodes. Okay? Therefore, all the k-mares are there. And we could choose to represent those k-mares by some of the nodes in the suffix tree. That's what we will do. So therefore, the nodes, explicit nodes, which are interesting for us, are nodes which represent words which are larger or equal than k, and whose father represent a shorter node than k. Okay, this is the first node on its branch represented a k-mare. Okay, and below you have extensions of these k-mares. Okay, we will call those nodes initial nodes. Okay, if the initial node has exactly length k, this is a special k, we call it initial exact node. And if it's shorter than that, of k-1, we say subinitial. Okay, just before the level of k-mare nodes. Okay, so here, the same example with the initial node representing k-mares in gray. So you will have, for instance, I will focus. This is those three are initial nodes in gray. Some of them are of length 2. That's an additional exact node. It represents BA for k equal 2. And some of them, like BCAA, represent a word of length 4, but the prefix of length 2 is the only BC is represented also by this node. Is that okay? This is an initial node. And of course, is Faber here represent the word B. This is subinitial. This is length k minus 1. Okay? So obviously, we can get an isomorphism between those set of initial nodes and the k-mer we want to represent in the Durbin graph. So we could replace one by the other. So this gives us the node of the Durbin graph. Now, how do we get the ages? Okay. We have suffix links in the suffix tree, and that will help us compute the ages. So the age, if you take an initial node, okay, basically, if you follow the suffix link, you will lose the first symbol. And therefore, you get to its suffix of length k minus k, the initial length minus the first symbol. And then, if it's not a k-mer you have at the end of the suffix links, you have to go down the tree a bit of one age maximal. And then you will look at the children, and you will see the right extension of this suffix of this k-mer, and you will get the node, the target node you want in the Durbin graph. Therefore, you have to travel very little in the suffix tree to find those age. And you have to check a few things. For this, we need an important property, which will, why it will come clear later on. In a suffix tree, you will have a suffix link if you have a node U and a child V. Okay, and the suffix link of U go here. Then the suffix link of V must go in the subtree of this node, necessarily. Okay, and I will use that later on. So this is a simple property. Okay, now I will take you, there are 4 cases you can consider for finding the age of the Durbin graph, and I will show you all of them with examples. So the starting initial node would be in green. The suffix links would be of this node would be in with this type of arcs, and after we have found the target nodes in the Durbin graph, we will put color ages for the Durbin graph, okay? So the color age, that's the thing we want to find. Okay, so the first case is the initial node is of size not exact, larger than k, and in fact, the suffix links point directly to an initial node, and then you are done, because you are already in the set you want to be. Okay, so that's nothing to check, only the size of the target node. This is type 1. In the type 2, the initial node is not exact, larger than k, like here. Okay, 1 is a much larger word than k equal 2. Its suffix links go deep in the tree, and you want to find the first node on this branch that represents a k-mer, the initial node of this branch. So we should have, at some point, a pointer going to the target of the suffix link to the k initial node ancestor of this node. Okay? This is type 2. If you have exactly an initial node as a starting point here, the starting point is exactly of size 2, AC. Okay, the suffix link points to C, and therefore, depending on the number of children of this node, you will know how many targets you will have here. Here you have only tape 3 is when we have only one possible right extension of this k-mer. So the following is A, C, and B, and therefore the children of this node that you need to take as a target of the Durbin graph age would be the one followed by B and not the one followed by AA. Okay? So type 4 is exactly type 3, but in the case where the starting node, okay, has several children. We're exactly in the same situation, but we have to distinguish for later on. So initial exact with several children, and then, okay, so in our example, the initial node is starting initial node here, the suffix link goes up, and then we have 3 children, therefore there are 3 extension, possible extension, and 3 neighbors in the Durbin graph after this node. Okay? It's 10 minutes, about? Sorry. Okay, wonderful. Okay, is that all right? Any question here? Yeah, but I want to be sure people can follow. So we have 4 types, I think, and all of them can be processed quite easily. Therefore, we will have, from the generalized suffix tree, we can get the construction of the doubling graph in a time which is linear in the size of the input set. Okay? Why? Because all 4 cases of the topology for finding the edge can be processed in constant time, provided for case 2, you have this pointer to the ancestral node of size representing a k-mer on its branch. Okay? But a single traversal of the tree will give you that. Okay? So we've got the first part. Now, when you use assembly doubling graph, usually you want to search for simple paths that will represent contigs that you will give to the biologist back as a part of the sequence that you were able to assemble. Okay, so to reduce the size in memory of the assembly graph, people contract simple path. So here's, for example, the contracted doubling graph for k equals 3. And you see that here, when you start from CBA, you have 2 possible locations. But if you take this path, then you end up on a simple path where you have no choice. There is no branching here. And therefore, until you come to AAC, all this path is determined because there is no choice. If you start in there, you have to go there. Okay? Therefore, all the intermediate nodes in this simple path, when you leave the first node, which has at least an out degree of 2, and until you reach a node with an in degree of at least 2, okay, you will have all those nodes can be concatenated in single node, which is done here. So, and it's not concatenated, it's agglomerated with their overlap. Therefore, you will have BAB followed by a C. You always keep the last symbol because you all add 1 symbol at a time. A. It will give you BABCAA. And this node does not represent a k-mer, but something larger than a k-mer. Okay? So the thing is, there is another simple path here, and you can also compress the interior of the simple path in a single node. Okay? So how do we find on the fly such situation where you can build the edge and agglomerate the edge while finding them? Okay, if we want to construct a contracted double graph in a single algorithm. For this, we will need 2 definitions. Find the nodes in which you can agglomerate the next neighbor or not. Okay, and this will be left extensible. A node will be left extensible if the in degree is 1, and it will be right extensible if the out degree is 1. So you have only one choice to get out or only one choice to get in. Okay? And then you have no branching. You can make a single edge between those nodes. Okay, this is the formal definition of the contracted doubling graph. Now we'll see how we can get those information. So the initial nodes, the right extensibility. Can we find right extensibility? That's why we distinguished 4 types of edges in the computation I've shown you before, because the initial node, if you have type 1, type 2, type 3, if you remember, you only have 1 possible extension in the set of words. So this k-mer was always followed by the same letter in all occurrences. Therefore, you only have 1 extension, and if you have 1 extension, you have only 1 outgoing edge, and therefore you're right extensible. The last case, type 4 case, you have several children and therefore several extension. And if you have several extension, you have several edge going out, and therefore you're not right extensible. So if you know the type of edge, you know if you're right extensible or not. Okay, that's explanation. I think this is quite easy to follow. Now an example. An example here that you have this node, okay? You have this branch, and therefore you ask whether 4 is right extensible, but 4 this edge, you have only one extension, therefore there will be only one edge going from 4 to 5, and therefore here the red 4 will be right extensible. Okay, and it's also the case here until you get here. Okay, so there is a simple path that we can find here. Is that okay? Now the left extensible. That's why I use the property I've shown you before. We will look for left extensible node if we are on right extensible. Okay, we are creating a simple path, we are visiting a simple path, and we want to create the edge. We delay the creation of the edge until we find the non-left extensible nodes. Therefore, we have to check that. Okay. So we start from the right extensible, and we have V is the right extensible node, and we have an arc VU, and want to know if U is left extensible or not. Okay, we have this lemma, this property. U is left extensible if we can verify this. So I will explain you what this means. Okay, so this is V, an example, and this is U, and you are traversing this edge, and we want to know if it's right extensible or not. All the occurrences that are suffixes correspond to the numbers in the subtree of U. So there are 6 of them, column numbers. Okay, 4, 5, 2, 2, 2 of different colors, and a 1. The 1 is a terminal node because it is as a starting suffix of one of the input words. Therefore, it has no predecessor in this word because it is as a start. And therefore, for this number, we are not expected to have an edge coming in on this node. But for all the other, okay, we have to know where they come from. Where are the ancestors in the tree? Therefore, we have this. The set of V suff of U is all set of suffixes which have U as where U is, and we have all those 6 column numbers. And you remove the terminal one because it has no predecessor. And the question is, where do the suffix links of those nodes come from? If they all come from the initial node you are starting from, it's okay. Then you're done because all extension of this one are extension of this one. All extension of U are coming from extension of this starting node. And therefore, you have the equality, and therefore it's left extensible. So in this example, it's not the case because V suff of U minus V ter of U is not equal to V suff of V, which is only 1. Okay, it's only the 1 orange here. Okay, the 1 orange explains why the 2 orange is here, but it does not explain why the 2 red, 2 blue, 4 black, and 5 orange are here. Okay, so all those extensions are not explained by this node, and therefore this node would not be left extensible. So I can show you this in a general manner, this lemma here. So you start from here to here, and you have all those possible suffixes there. Some of them might be terminal nodes starting of some input words, and you delete them, but you have to explain all the black ones remaining black. If all the suffix links coming onto those black nodes here in the subtree come from the subtree of the starting node, you're done. You're left extensible. U is left extensible. If it's not the case, okay, you may have some red dots where the suffixes don't come from the starting, so the subtree of the starting node, and in this case, it comes from elsewhere. And this would mean you have several edges entering the U, and therefore you cannot be left extensible. And then you're done. Okay? So an example here, okay, U is this one, and you see you have the green edge coming from 5 green coming here, and the 1 orange coming inside here. Okay, so if you start from this one, you have to check whether those 1, 2, 3, 4, 5, because you remove this one, can be explained by the suffixes which are in this subtree. And here there are only 4. Therefore, they cannot explain this with their suffix link all those 5. And this is because the suffix link of this one is going in there. Okay? So, with all this, we can get the contracted doubling graph in linear time from the generalized suffix tree, because the dissection of the right extensible nodes is obtained directly from the 4 types. And while you're preprocessing the tree, you can compute V sub u and V ter of u. You only need the size of those set. And for each node, for each appropriate node, in linear time, by going through the generalized suffix tree only once. And therefore, you can get those information of right and left extensibility while going through the tree, and therefore you can construct your contracted doubling graph. Okay, so what we have, the result is a new linear time algorithm to construct a contracted doubling graph directly from some standard data structure. And what you can do with a generalized suffix tree, you can also do with generalized suffix array and with other data structure, but only one is detailed in the paper. The result for the suffix array are also there, but very minimal size. And we have many open questions. Of course, in the generalized suffix tree, we use mainly only a slice of the generalized suffix tree. We don't use all nodes. Okay? Therefore, it would be nice not to construct the whole tree, but to have a restricted data structure showing only some of the nodes you need to do the whole work. Okay? This we have been working on since the submission. The other nice thing is that with this system, you can update K. If you're not happy with K, because K at some point is too short for some overlap, you can go to K plus 1 easily or to K minus 1 easily. This can be shown quite nice. And of course, it becomes a bit more complicated, more tricky to describe the algorithm if you go for compressed index instead of standard index, and it's not so easy to display in a talk. There are also some open problems related to computational biology questions, but I won't detail that. I want to thank you for your attention. And if you have any questions. Okay, this is our support.
Are there any questions?
Yeah. I wonder why you need, or do you need to materialize the Bruijn graph? Because you could simply use the compressed suffix tree and take the nodes of the suffix tree, the pre-order, for example, as the identifiers of the nodes of the Bruijn graph. And it seems that if you can solve your 4 cases in constant time, then you can build on the fly the edges when you need to navigate it, even backwards, it seems, with Wiener links. Does that make sense or not?
It depends what you want to do with it. If you only want to traverse and find the sequence, yes, if I have this good in mind. If you want to know from which read you are assembling to get this sequence, then that's a bit different. Because you will like to keep some position information about which input words are you coming in. Yeah. Currently, people are working a lot on compressed representation of the Bruijn graph, as for instance Gregory has done, where you only allow the traversal and you lose the visibility from which input word you were coming.
Yeah, actually, I have a question also. So, so if the data is very repetitive, or if the reads are very redundant, so the Bruijn graph is considerably smaller than the suffix tree. Okay. So your algorithm, is it the complexity? Is it proportional really to the input data or to the output?
it's here we state the complexity. If you have to read the input data to make the suffix tree. So here, if you go for a suffix tree, you will be proportional to the size of the input data because you have to read it. Okay. In fact, if you use only part of the suffix tree, if you reduce the suffix tree and you consider some anti-chains, because the k-mer node, the initial nodes represent an anti-chain through the tree, and a certain slice defined by some anti-chain, you can be proportional to the size of the Bruijn graph. Does it?
Yeah, okay.
Yeah.
No more questions? Okay, thank you again.